Hello class 12th. In the last lecture, we had concluded with the topic refraction through multiple media, and this was the equation. Now, I want to say that equation can be also written in this form. Suppose to find the refractive index of LNG. So LNG means the refractive index of glass with respect to liquid. So if it is there, so at that time LNG, the refractive index of glass with respect to liquid, can be written as the refractive index of second medium upon refractive index of first medium, means the refractive index of glass upon the refractive index of liquid. So let's start our new topic, the relation between the real depth, apparent depth and the refractive index. We can experience when we lower in the swimming pool, we can feel the apparent depth of the swimming pool is less than the actual depth. And the same you can experience when some card, visiting card is placed under the glass table. You can feel the same experience. It all depends on the density of the medium, or you can say the diffractive index of the medium. For that, let's see the relation between the refractive index, the real depth and the apparent depth. For this, consider a container in which any second medium is there. We can say a liquid or water. That the water has the refractive index A and W, and an object is at the bottom in the beaker. You can consider a coin, naming with point O, and the light falls from everywhere on this object, and when the light comes out from this medium received by any person, that person will feel the apparent depth of this object. So I am drawing the two rays. So here it is, the one ray OAB going through this path OAB, and the second ray. Now this another ray, suppose this is going OC. The ray OAB was falling normally, changing the medium normally, so there was no refraction, but the ray OC is changing the medium at any angle, so here will be refraction. So let's draw normal NN dash, and let's draw the angle of incidence as it is changing the medium. This is the angle of incidence. As the light is going from denser to rare, it bends away from the normal. Now let's draw backward where the image will form, because someone will see at this from this point, so where the object will appear. Let's draw the image. So for the person who observes this, for him or for her, this object which was lying at the bottom will appear at this point. This will be the image for that. In this diagram we can say this ray and this ray are perpendicular on the surface, so they are parallel. So this angle I and this angle must be equal, means this angle will also be angle I in the same way by the corresponding angle, the angle R, and this one angle here will also be R. Now the light is going from denser medium to rare medium, means water to air, so we will write WNA, and in the W medium, means water medium, the angle of incidence is I, angle of refraction is R, so you can say WNA is equal to sin I by sin R. Let's write here. You can see here the I is forming in the medium W and R is forming in the medium air, but whenever the refractive index will be given, that will be given in with respect to air. So this is WNA. To make it A and W, we will follow the principle of reversibility, means the reciprocal of it will be the refractive index of water with respect to air. On reversing that, see here WNA was sin I by sin R, so A and W will be sin R by sin I. Let's put the value of sin R. So sin R means the triangle IAC. In this triangle, sin R is equal to perpendicular AC upon hypotenuse IC. So let's write that. So here it is, sin R is equal to AC upon IC, and sin I in this triangle OAC, again sin I is equal to perpendicular AC upon OC. Let's write that. So you can see AC upon IC for sin R and AC upon OC for sin I. AC is cancelled. On solving that, A and W means refractive index of water is coming with OC upon IC. So let's see what is OC. OC means O to C, this distance. If the aperture of I, as we know, is very small, so we can consider the point A and point C are very close for the small aperture of I. So instead of OC, we can write OA, and instead of IC, we can write IA. Let's change that. So I has a very small aperture, so point A and C are very close to each other. So on changing that OC upon IC, so that OC changes to OA and IC changes to IA. So what is OA right here? That was OC, now it is OA, and IC, now it is IA. The OA was the real depth of the beaker, while the image of this coin is come to here. So this is the apparent image. So the real depth is OA and apparent depth is AI. So this OA is the real depth and IA is the apparent depth. On putting the values, the refractive index is equal to real depth upon apparent depth. But in examination, sometime the question has the information that the shift or displacement, also it is also known by displacement, the shift will be given, means the value of IU will be given. How to calculate this shift? Let's do that. Real depth minus apparent depth will be shift. Let's write that. That shift is equal to real depth minus apparent depth, that is AO, the real depth, minus IA, the apparent depth. Taking AO common, it makes one AO bracket 1 minus IA upon AO. Here it was OA upon IA. Here IA upon AO means the reciprocal of this refractive index. We can write 1 upon A and W or WN A. Let's put that. So shift is equal to AO bracket 1 minus 1 upon A and W, or AO bracket 1 minus WNA. But in any question, WNA will not be given. A and W will be given. And AO, the real depth, can also be considered as AO, can also be considered the thickness of the medium. So on putting that, let T is the thickness. So we have the shift, which is also known as normal displacement, is equal to T bracket 1 minus 1 upon the refractive index of the medium. So we have seen the relation between the refractive index, real depth and apparent depth, that N refractive index is equal to real depth upon apparent depth. But there was single medium with respect to another medium. But suppose there are multiple parallel media, means like this. At that time, what will be the relation between the refractive indices? Let's see. Considering these three parallel media of refractive indices N1, N2, N3, with the thickness of the medium is D1, D2, D3, then by the equation N is equal to real depth upon apparent depth. Let's find the real depth now. Real depth is from here to here, means real depth will be D1 plus D2 plus D3. Let's put that, which is D1 plus D2 plus D3. Now apparent depth. Apparent depth depends on the medium's refractive index. So this one is having N1. So for this medium, the apparent depth will be different, and for them will be different too. So let's calculate first the apparent depth for this medium using this equation again. N is equal to real depth upon apparent depth. So apparent depth will be equal to real depth upon N. For this medium, as refractive index is N1, so the apparent depth for this medium will be real depth for this medium upon refractive index of this medium. So I'm writing here, see, for this medium, only for this medium I'm writing apparent depth, real depth for this medium upon refractive index for this medium. Same for this one also, D2 by N2 and D3 by N3. So on writing the apparent depth for all these media, the equation will be, this will be the final refractive index of the medium. So D1 plus D2 plus D3 real depth becomes, and the apparent depths D1 upon N1, D2 upon N2, D3 upon N3 are the apparent depth of this media. Now suppose if there are furthermore some medias are there, still the equation will be same, plus D4 plus D5, same way D4 upon N4, D5 upon N5, and so on. Now our new topic is the critical angle and the total internal reflection. This is nothing new for you. You have learned about it in class 10th as equation for the critical angle. The refractive index is the reciprocal of sine of critical angle. So when the light goes from the denser to rarer, it's a particular angle in the denser medium for which the angle of refraction becomes 90, like this diagram. And the total internal reflection says it's a particular angle in the denser medium for which the light reflects in the same medium. So this is called total internal reflection. So there is a two condition. Condition one, that light must travel from denser medium to the rarer medium, and second, that angle of incidence must be greater than the critical angle. Now some examples, some daily life experience about the total internal reflection is like mirage. See here, a person can see his own image in the desert when the light travels from denser to the rarer medium. Then it totally internally reflects and the image forms inverted image, and the person feels that there is some lake or a source, some source of water. So this type of experience is due to the total internal reflection. Next is brilliancy of diamond, and you can also deviate the light to 90 degree, 180 degree, and you can erect the object. And the important topic which used to come in examination is optical fiber. Optical fiber, sometimes also called light pipe. You can see the optical fiber is used to transmit the light. Not only light, it can transmit the audio signal also. It is used in the telephonic purposes. That cable are used to transmit the audios, and now they are used to call optical fiber. The data net, internet are running on these fibers, and on this optical fiber is made up of two type of material. One is called core and second one is called cladding. Core has more density than the cladding. The inner one is core and the outer one is cladding. When the light goes from the core to cladding at a particular angle, it reflects in the same medium, means the total internal reflection phenomena is going on. So the audio, the light or any signal is transmitted from one end to another end. If suppose the wire is bent, this optical fiber is bent like this, but there is no change in the signal processing. The signal receives at the same angle at which you are transmitting in the optical fiber. This fiber is also used in the endoscopy, when doctor used to put some camera and the light inside you to find the image of the stomach. Inside the stomach, they put some camera with optical fiber wire to get the image of internal organ. This process known as endoscopy. But now we are completing our chapter, and let's move about the numerical. I will solve only two, which was asked in the question in the board examination only. So let's see the questions. Now, see, a numerical came in 2014. A narrow beam of monochromatic light is incident on one face of an equiangular glass prism of refractive index 1.55. When the prism is immersed in a certain liquid, the ray makes a grazing emergence along the other face. Find the refractive index of this liquid. So this is the diagram where the light ray is falling on a glass prism, and this prism is immersed in a certain liquid, and the light ray goes to this bath. So let's draw first the medium liquid outside this prism. Now consider this prism is placed inside the liquid. These lines are showing the medium in which this glass prism is placed. As in the question, it is given that equiangular prism means this triangle, this prism is equilateral prism and 60-60 having each angle. So this angle is 60, the light is coming on normal. Normally it goes to this. So this is 60, this is 90, this one will be 30, and the remaining angle becomes 60. So this angle becomes 60, and you can see the light is grazing the surface, means this is the critical angle and this is 90 degree. So we can say the light is going from the glass to liquid. In the glass the angle is 60, and in the liquid the angle is 90. Let's write the equation first. Sine 60 upon sine 90, GNL. The light is going from glass to liquid, So GNL will be equal to sine 60 upon sine 90. In the starting, I told you GNL means the refractive, it is the ratio of two refractive indices, the refractive index of liquid upon the refractive index of glass. This can be written as, so here it is, the second medium liquid ANL, first medium glass ANG, sine 60, sine 90. And the question says, find the refractive index of this liquid, means we have to find what? ANL. We are having the value of ANG. In the question it is given 1.45, and the value of sine 60 and sine 90 we can write it. So on writing the value, here it is. On further solving, the refractive index of liquid comes to 1.26. See another question, question number 3, fall in 2002. A ray of light which is incident in air on the surface of a glass block is deviated through 15 degree. The angle of incidence in air is 60. What is the angle of refraction in glass? Also find the critical angle for glass. So first of all, let's draw the ray diagram. This is the glass block. According to the question, the angle of incidence is 60 in air. After refraction, the ray goes through this path, and we have to find first this angle of refraction. But one more thing in the question is given, that light ray is deviated through 15 degree, means the angle, the original path and the refracted ray has the deviation of 15 degree. Let's draw that. So you can see this is the original path, and this is the refracted ray, and this is the deviation 15 degree. So we can see here this normal and this the original path are forming X. So we can say this total angle is equal to this 60 degree by the vertically opposite angle, means 60 is equal to R plus 15. So here you can see 60 is equal to R plus 15 using this diagram. So R is equal to 60 minus 15 and R is equal to 45 degree. The first part of the question done. The next part is to calculate the critical angle. We know that refractive index is equal to 1 upon sine C. So first of all, we have to calculate its refractive index, and then with the critical angle. We are having this equation can be written as, now the angle of incidence, the light falls on 60, the angle of refraction is 45, means we are having the value of sine I and sine R. Let's put that. So sine 60 upon sine 45 is equal to sine C. On reciprocating it, you can also say this thing. On putting the values, we are getting this. Sine C is equal to this. On using scientific calculator, it gives critical angle 54.7 degree. Now we are moving to our next chapter, chapter 16, the refraction through spherical surfaces. In the last chapter, we were studying about the refraction through plane surfaces. Now we are going to study about the refraction through spherical surfaces. Let's see, the first proof of this is on the spherical surface. Now let's see the refraction at concave spherical surface first. Consider this concave spherical surface, and this is the denser medium. Taking this line as a principal axis passing through the pole P, taking C as the center of curvature, SS dash the surface, and here O is the object on the principal axis, and it will form an image because it's a denser medium. So if it is going to form an image, so we need at least two rays. So I'm considering one ray which will go through this path OP, and the second ray towards this surface. So the first ray OPQ, and the second ray is going OA. But now the light is changing the medium, so we need at least normal, and we know that the normal will pass through the center of curvature. Let's draw that first. Now CN is the normal, and the light ray is going to the denser medium, means definitely it will bend toward the normal. As you can see, the OA ray bend to AB, marking the angle of incidence, the angle of refraction here. See, so here the angle of incidence, and there is no space, so I'm writing here the angle of refraction. So another one, where will be the image form? So the image will be appear if we draw the backward to this position. So the image will form somewhere here. Let's draw that. Now see, the image of the object is forming here, virtual Okay, now let the angles forming this one, this one, this one, say this one is alpha, image making beta, and the C is making gamma. So gamma and R will be very similar to them, to each other. So I'm changing this symbol R and this gamma as gamma. Whenever I'll draw gamma, I'll draw in this form, and whenever I'll draw R, so I will draw like this. Okay, now the angle of refraction symbol is this, and gamma has symbol this one. So this one is having the angle alpha, this one is having the angle beta, this one is having gamma. Now see, this line is coming in straight and this line is coming straight, means they are forming X. So this angle R here is equal to this angle, vertically opposite angle R. Again, I want to inform you, like in the last lecture, we had proved that relation between, yeah, okay, or you can say mirror formula. In the same way, for this surface, we are going to find the relation between U, V, the radius of curvature R, and the refractive index of the medium too. So let's draw the distances first. As we know that all the distances must be measured from pole. So this is R, this is image distance V, and this one the object distance U. See, in this triangle, triangle OCA, in this triangle, the sum of this angle alpha and I and this one total makes 180. And the exterior property says, exterior angle property says, the sum of two interior angles is equal to the exterior angle, means the sum of alpha and I is equal to gamma. Let's write that. See here, the triangle OCA, alpha plus I is equal to gamma, or I is equal to gamma minus alpha. Make it equation 1. Now again, triangle OIA, same way, sorry, not OIA, ICA, in this triangle. In same way, using the exterior angle property, the interior angles are beta and R, and the exterior again gamma. Now in the triangle ICA, writing that, see here, in triangle ICA, beta plus R is equal to gamma by exterior angle property. So R is equal to gamma minus beta. Now using the Snell's law that says the ratio of sine of angle of incidence to the sine of angle of refraction is a refractive index of the second medium with respect to first medium. So I'm taking the refractive index of this one is N2 and the refractive index of air is N1. It doesn't matter that, only you will write 1 N2 or simply N2 upon N1. So we can say the sine of angle of incidence upon sine of angle of refraction is equal to N2 upon N1 in the equation form. See here, sine I by sine I is equal to N2 upon N1, or N1 into sine I is equal to N2 into sine R. Now put the value of I and R from equation 1 and 2 here. But before that, I want to inform you, for the small aperture, this sine I is tending to I only and sine R is tending to R only. For small aperture, sine I for small angle, sine theta is tending to theta only. So I'm writing that if theta is tending to 0, so sine theta is equal to theta. Okay, sine I is equal to I, sine I is equal to R. Now put the value of I and R from equation 1 and 2. Using equation 1 and 2, now here it is, gamma minus alpha I, gamma minus beta R. Now opening the equation bracket and taking gamma on one side. Now see, taking this N2 beta to this side becomes positive N2 beta and N1 alpha on the same position. N2 gamma is on the same position, minus N1 gamma is coming in this side, N1 gamma, taking gamma common, so N2 minus N1 gamma, left side remain same. Now draw a perpendicular from A to this principal axis, say this is M of height H. Since this M and P are very close to each other and we are having the angles alpha which are so small, so we can take alpha is equal to tan alpha. How? See here, see in this triangle OAM, in this triangle tan alpha perpendicular upon base. So I'm writing AM 10 alpha. See here, alpha is equal to 10 alpha. This angle is so small, so alpha is equal to 10 alpha. AM upon OP. OP because M and P are very close. So instead of writing OM, I'm writing in direct OP. So put the value of AM and OP. What is AM? AM is the height. And what is OP? OP is the distance of the object. That will be negative by sign conventions. So on writing here, the value of AM is H and the value of OP is minus U. Same way, I'm writing for the beta and gamma. See here, beta is equal to 10 beta, AM upon IP means H upon minus V. And the last gamma is equal to 10 gamma, AM upon CP is equal to H upon minus R. Why minus? Because all the distances are on the left side from the pole. So all the distance will be, this will be negative. Now let's put all these value of alpha, beta and gamma in this our last equation, that was n2 beta n1 alpha n2 minus n1. Let's copy it here first. As you can see here, this was the last equation. Putting the value of beta H upon minus V, alpha H upon minus U and gamma H upon minus R. See here, every term has a negative sign, so all will be cancelled, and H is also common in all. So H and negative sign both will be common, cancelled. Let's see what will be the next. See here, H and negative sign cancelled. What will remaining? N2 by V minus N1 by U is equal to N1 minus N2 minus N1 by R. Sometime in the board examination, it is used to us to prove this equation using either concave or convex spherical surface. This is the first proving in this chapter. But in the starting, I told you this is the refractive index of the second medium with respect to first medium will be the refractive index of this glass. So we can say that here the refractive index of glass N is equal to the N2 by N1. The refractive index of this glass can be written as N2 by N1. N1 is air and N2 is glass. So using this concept, I am dividing all the upper numerator with N1. Let's see what will happen. See, what is the change? N2 by N1, N1 by N1, N2 by N1, N1 by N1. I have just divided with N1. So this N1 upon N1 will be cancelled and this N1 upon N1 will be cancelled. And N2 upon N1 was equal to general N. Now, N by V, because this is N, minus this is 1 by U is equal to N minus 1 by R. Sometime in the board examination, it is also used to ask and very important for the board examination. Now let's move the numerical on this topic. Now one question based on this equation. A convex spherical surface of refractive index 1.5 means value of N forms the image of an object distant 10 centimeter means value of U. Form it at distance 40 centimeter means value of V. What is the radius of curvature? Question, what is R? So I'm taking the convex spherical surface because I haven't found any question on concave spherical surface as we have proved on it. So if you will prove using convex surface, the same equation will come. So for this surface, I'm writing first what is given. So you can see the value of U 10 centimeter, value of V minus 40 centimeter, value of refractive index 1.5 and question mark means R you have to calculate. Let's all put all the values in this equation. What we will get? See here, N 1.5, V minus 40, U minus 10. Now we are going to calculate the value of R for the convex spherical surface means surface must be like this and the radius of curvature for this surface will be positive. So point must be remembered that the R must be a positive in the answer. So let's calculate for the, sorry, that will be 4. 0.5 will cancel this 5 times. So and negative is cancelled. So now finally what you got, R is equal to 8 centimeter and this is positive means our answer is correct. So I'm concluding this lecture here now and I'm giving you a task for to prove that equation using the convex spherical surface and do some numericals. In the next lecture we will discuss about the lenses and further more. So till then, thank you all for watching my